Hello, hi, welcome back to Classical Mechanics, Physics 411, and I'm still your instructor, Sasha Chikhovskoy. This is the first part of Lecture 7 in this course, and I'm going to start with a brief recap of what we did last time. Last time, we covered a bunch of things. First off, we started with a two-body problem. Namely, it's a motion of two bodies of mass m1 and m2 around a common center of mass. It turns out that we can show that the Lagrangian that describes the system is identical to a particle, a point particle of mass mu, which is called the reduced mass, that is moving on an orbit in a fixed potential v, which is the same one that describes the interaction between the two point mass particles. So it turns out that this system is actually equivalent to a motion of a particle of mass mu in a potential that is fixed, that is v of r. And in the case of Keplerian, we can write down that the mass of the central object is the sum of both masses, and the potential is given by minus k over r equal to minus g m1 plus m2 over r. So k is given by this numerator, g times the sum of the two masses. What is really cool is that this motion of this binary system of two masses orbiting each other is actually two-dimensional. That's because the angular momentum of the system is conserved and the motion is perpendicular to the angular momentum vector. So the motion will be confined to the plane perpendicular to the angular momentum vector, and so the motion will be two-dimensional. That is why we can reduce it to a 2D problem with just 2 degrees of freedom. And Q1 and Q2 are equal to r and theta. So what other cool things have we done? Well, we've also shown how to obtain the shape of the orbit in time. How does the orbit depend on time? So we have been able to do that by integrating the equations of motion most of the way. So we did that by relying on two integrals of motion. The momentum, which is r squared times theta, and the energy, which is 1/2 of r dot squared plus r squared theta dot squared minus v of r. And here, for simplicity, we have assumed the value for mu equal to 1. It really doesn't affect any results. By dimensional analysis, you can always figure out where you need to stick in an extra factor of mass, and then you can resurrect it back. So this is just to not keep mu around. So with these two, we actually can combine them together and obtain a very useful form of the differential equation that describes the motion of the binary system in a Keplerian potential, or in a more general potential given by v of r. And this is a very convenient form because if you integrate it, on the left-hand side you only have an integral that involves time. On the right-hand side, you have an integral that involves radius. So we can integrate the right side separately from the left side. So on the left we have a function of time, on the right we have a function of space. So this gives us immediately a expression of r of t, and we can also go from here to theta of time as well. So this gives us a very simple way of constructing the orbit as a function of time. So this actually has a name. What we've done here is we have reduced the problem to quadrature, or we have obtained the orbit in time. Because integrating such equations is a piece of cake, nowadays, if you are able to reduce a problem to quadrature, it's as good as having obtained essentially an analytic solution. So this is awesome because it's so easy to obtain the actual solution by integrating it, if not analytically, then numerically. And finally, by making use of another form of the equations, we have been able to obtain how the shape of the orbit in the central potential depends on the physical parameters of the orbit, such as the angular momentum and the energy. So for that, to obtain orbit in space, we actually used a different shape of the equation, which is the radial force balance equation, where r double dot is given by the centrifugal force minus dv dr. So that is the gravitational force or another force that mediates the interaction between the 2 point masses. In the case of Keplerian motion, in fact, we can rewrite this by plugging in the gravitational potential and get this relationship. Using a substitution, u equals to the inverse of r, we have been able to integrate this equation of motion in order to get the shape of the orbit. And we're going to discuss this in the next part of the lecture. Thank you very much for watching, and don't forget to do the quiz. I'm going to see you soon. Hello, and welcome to part 2 of lecture 7. Here we're going to finish up the recap that we started in the previous part of our lecture, right over there. So what have we been discussing? We've been discussing how to obtain the shape of an orbit in space. So how does an orbit look like in the Keplerian case? Well, it is an ellipse with the focus of an ellipse where our central potential is centered. So that is r equal to 0. And we will have a semi-major axis that is 2a long. A is our semi-major axis, so this is the length of this ellipse is twice that. This part of the ellipse is a times 1 plus e, where e is the eccentricity of the orbit, and this part of the ellipse is a times 1 minus e. So the only difference is plus or minus sign. This point is called the apocenter, or apoapse, or apohelion. This one is called pericenter, or periapse, or perihelion. The tilt of the ellipse is parameterized by omega, and the position of the particle on an orbit is parameterized by an angle theta. So if a particle is in orbit somewhere here, there will be two parameters that control that. R is the distance from the center of the potential, and theta is the angle, is the polar angle. So the shape of the orbit that we are able to obtain is R equal to A times 1 minus epsilon squared divided by 1 plus epsilon times cosine theta minus omega. So as you can see, when theta is equal to omega, cosine is equal to 1, and then the factors of 1 plus epsilon will cancel in both numerator and denominator, and we're going to get A times 1 minus epsilon, which will be precisely the position of the pericenter. So theta equal to omega is the pericenter. And then apocenter is theta equal to omega plus pi. So we're going to move over to the other side of our orbit. So that is the apocenter. So this is the correspondence between Cartesian and orbital element representations. In both cases, there are 4 parameters describing the position on the orbit: x, y, vx, and vy. And in the case of orbital elements, there are 4 orbital elements: a, eccentricity, theta, and omega. And so this is how you can go between the two. So from a, eccentricity, and theta with omega, you can get to r. You can also get to the velocity along the orbit, the theta component of velocity, which is related to the angular momentum, as square root of Ka times 1 minus epsilon squared. And finally, you can also get energy, which is 1/2 of v squared minus v of r, or on the other hand, it will be just minus k over 2a. And this term, 1/2 v squared, is simply equal to that, or equivalently, you can write it out as such. Great, so having this cheat sheet is extremely useful to be able to go from the desired angular momentum and energy, for instance, to the physical parameters of the orbit that control the geometric shape of it. So geometry, and then the angular momentum and energy. Let us now, while we're at it, derive Kepler's third law that tells you how fast our particle will be advancing on an orbit. There are multiple ways of doing that. We're going to be using geometric ways, since we have been talking about geometry. For that, we would need to remember some basics about how an ellipse looks like. So let's draw another ellipse. This time we're going to draw it aligned with our horizontal, and let's draw 2 lines like this, the x and the y lines. So what is important here is that these two are semi-major axes and these two are semi-minor axes. So that is how the aspect ratio of the ellipse gets set. So if eccentricity, for instance, is 0, then A is equal to B, and we've gotten a circle. If eccentricity is 1, well, then our ellipse will stretch out. So that is how we know the mapping between eccentricity and the geometric shape intuitively. So let's try and figure out how fast does our point advance in time along this geometrical shape, which is the ellipse. Well, for that, let us compute the integral of all dt's throughout the orbit in order to get the period. We take an integral over the orbit of dt. How do we compute time from the geometry of the orbit? Well, here we can make use of the conservation of angular momentum, which is given by r squared theta dot. This is a constant. Therefore, we can pull out what d theta and dt are in relation to each other, and we're going to be able to find that L is equal to r squared d theta dt. So we can take the t out of here and plug it into there. So we're going to find that dt is equal to r squared over L times d theta. So this actually is nothing but the area element that a particle, as it moves in the orbit, covers. In fact, it's twice that. If we have a particle on an orbit that is a distance r away, its distance doesn't really change that much in one time step, at least for the purposes of calculating the area. The triangle that the particle's vector has covered will have an area that we can compute from right here. And this area, dA, is going to be equal to 1/2 of r squared d theta. With this, we can easily integrate this and obtain that the result will be just the area times 2 of our ellipse. But we know what the area of the ellipse is. It is pi times a times b. That's the area, where a and b are semi-major and semi-minor axes of the ellipse. And because we know how a and b relate to each other, namely that b is a times square root of 1 minus epsilon. This is what we're going to plug in there. We are going to be able to get the final result is 2 pi a squared square root of 1 minus epsilon divided by gma 1 minus epsilon squared. And you can immediately see that some things are going to cancel out, like this term is going to cancel out, and we're going to get the result that the period is proportional to the semi-major axis to the power of 3/2, just like for the circular orbits. So that's great. We have obtained the Kepler's third law through geometrical means, very elegant, and in the next part of this lecture, we're going to move on to the general central force. And I'm going to see you there after you do the quiz. Hello, and welcome to the next part of our lecture, 7, part 3. Now we're going to talk about general central force. So let us recall what we have been able to get so far. We have obtained the form of the Lagrangian, which is 1/2 r dot squared plus r squared theta dot squared minus v of r, where v of r encodes the general central force. The conserved energy of the orbit, which doesn't change, is, in this case, related to the Lagrangian in a regular way, as we have shown. And by eliminating theta dot, by using the conservation of angular momentum, which is given by this expression, L is equal to r squared times theta dot. We're able to eliminate theta dot from this equation in favor of the conserved angular momentum. Let me perhaps make use of the same color. So we are going to get that the result is 1/2 of r dot squared plus L squared over r squared plus v of r. So what we can do then is to combine these terms, these two terms, into an effective potential. So our total energy will be equal to the kinetic energy associated with the radial motion plus all of the pieces of potential combined. So this is going to be an effective potential. So this is effectively a 1D problem. So we've been able to reduce a 6-dimensional problem to just 1D problem, which is really remarkable. And not only it's a 1D problem, it's also a problem in the form of a conservation law. And these are particularly useful because you can get a lot of physical insight without actually solving ordinary differential equation that we're looking at right now. So let us use this to classify different kinds of orbits. Indeed, we can do this right away. So let us draw a diagram. So this is going to be radius. This is going to be energy of the orbit, E. And we're going to draw a typical potential here, this V effective, on this plot, because V effective is energy. And let's try and kind of get an idea of what it will look like. So at large distances, we will assume that this term wins. It will drop off slower than the centrifugal force. And the potential at large distances will be negative. So we will have something like this at large distances. At small distances, we will assume that the centrifugal force wins. So here at small distances, we'll have a dependence of 1 over r squared, and at large distances, we'll have a dependence whatever v of r gives us. For Keplerian potential, it will be just minus k over r, like we discussed previously. But now we're discussing a general potential. So somewhere in between, they have to meet. And this is a typical shape of the curve for a general form of the central force. So this is the centrifugal barrier. And there are a few other features that are particularly useful to discuss. First of all, notice that this is the zero energy orbit, so we'll keep that in mind. And the orbit here is of a negative energy. So that would be the minimum energy of this potential. And another thing to keep in mind is that we drew this for a particular fixed value of L. So let me note here that this is done for a fixed value of L. So for a particular angular momentum have we drawn this. If we change the angular momentum, then while the potential part will stay the same, this part will go up and down, and its shape can be obviously different. So let us consider the various kinds of orbits. There are 3 kinds of orbits. The first kind is those whose energy is positive. These ones are the unbound orbits. So these orbits they look like that. So suppose that we have a particle, comes from infinity, it hits the centrifugal barrier and bounces back. So that is an unbound orbit with energy greater than 0. So that's unbound. There is another kind of orbit which is E equal to 0. That is marginally bound. So this kind of orbit is right here. That is E equal to 0 orbit. And finally, we will have a third type of orbits, which is E less than 0. Those would be bound orbits. So these look like that. So this orbit will hit the centrifugal barrier on one side, and they will hit the potential on the other side. Finally, there is a special kind of orbit where the energy is the minimum energy possible equals to min. This orbit degenerates into a single point on this plot, and this will be a special case of a bound orbit, which is a circular orbit. So in all of these cases, the orbits are bound by the centrifugal barrier on one side, and in this case of a bound orbit, it's bound from both sides, between the values of r1, the minimum radius, and the value of r2. So we can visualize this sort of orbit because it's a particularly interesting one. Because the orbit bounces between r1 and r2, we can draw a circle of radius r2. We can draw a circle of radius r1, and then we can try and draw an orbit in between, so it could look like something like that. And the orbit doesn't have to be closed. In this other case, what we're going to get is, so this is the case of a bound orbit. In the case of an unbound orbit, we can also draw a diagram. Over here, what we're going to get is an orbit that comes in and goes out. And this is going to be this minimum radius of r1. This is supposed to be a circle. Great. Finally, let's discuss the marginally bound orbit. Here, it will actually look almost exactly the same as for the unbound orbit, except that once the particle gets out to infinity, so that the potential energy vanishes, if this effective potential vanishes and energy is 0, it means that the radial velocity will vanish as well. So in this specific case, a particle will stop at infinity. Whereas in the case of positive energy, it will be coasting. So this pretty much sums it up, and we can discuss the specific realizations of these orbits in more specific cases, for instance, for the Keplerian case. And I'm going to see you at the next part after you finish the quiz. See you. Bye-bye. Hello, and welcome to the last part of Lecture 7.4. We're going to talk about Varial Theorem. This is a very important theorem in various contexts. For instance, it allows you to interpret observations of galaxies and galaxy clusters because it tells you how the average kinetic and average potential energies are related to each other for a very generic situation that is very insensitive to the details of the system itself. So it's a very general, fundamental result that applies across a wide range of contexts. So let us try and get to it. So let us start with the equations of motion. dv dt is equal to minus the gradient of the potential. So remember that we had to do various things in order to obtain various conservation laws. For instance, when we did V dot into this equation, we got energy conservation. When we did R cross, we did angular momentum conservation. Here we're going to do R dot, and we're going to get the following: m r dot dv dt is equal to, actually let me rewrite these v's so that they look prettier and different than the big v's. Okay, so this will be dv dt, and this will be dv dt, and this will be equal to minus r dot gradient of the capital V, the potential. So what can we do here? As you might have used to by now, we're going to try and use the analog of integration by parts. So what we can say is that this is equal to u, and this is equal to v dot, right? And we can say that u times v dot is equal to u times v dot minus u dot v. So we can do exactly that right here. And what comes out of this is ddt of u times v. So u is going to be mr, and v will be the regular v, which is very convenient. And then we're going to subtract off from here u dot times v. So u dot will be mv, and then times v will be times another v. So this will be just v squared. And on the right, we're going to get simply a gradient in the radial direction. So it will be r dv dr. So what can we do about that? Well, let us try and average this equation over a very long period of time. So average we will denote by a vertical bar. So vertical bar over something is equal to an integral from 0 to a large value t of that something dt, and divided by the period of time itself. So integrate over time and divide over the length of time. So that is the average that we denote by a vertical bar. So if we do such an average, so we try and apply this averaging to every term in this equation, then this term will average out to 0 because it's a full derivative in time. So when we integrate it in time, we are going to get the difference between this term at the large time minus this term at the initial time, divided by the full time interval. And if the radii and velocities of the system are bound, so if we consider in a bound system that's kind of relaxed and in steady state, then r and v, they're always going to be finite, and the dot product will always be finite. So no matter what those values are, provided that we've taken a long enough averaging interval, we're going to divide a finite value at the top by as large a number t as we like, because we're free to choose as long an interval of integration as we want. And so once we've done that, then we're going to get that this term vanishes, and then this other term is going to give us minus mv squared average. So this will be an average value of twice the kinetic energy. And on the right, we're going to get minus r dv dr average. So what are we going to do about that? Well, let's take the special case of Keplerian potential. In that case of Keplerian potential, we can compute what r dv dr is. It's r, and v is minus k over r, so it will be equal to k over r squared. One of the r's goes away, and we're going to end up with minus v itself. Since that is the case, we can plug this in here, and now we're going to say that this is for Keplerian potential. We're going to get that this is going to be minus twice the average kinetic energy. That is going to be equal to minus v. So this will be plus v average. And so in the end, we're going to get that twice the kinetic energy plus the potential energy average adds up to 0 for Keplerian case, for Keplerian potential. And so that is the Varial Theorem, that the kinetic energy is minus half of the potential energy. Please note that there can be a numerical prefactor for the cases when the potential is not Keplerian. For instance, in galaxies, the potential can deviate from Keplerian because of the presence of dark matter and gas. So this relationship will not quite be that. There will be a numerical prefactor right here that will translate into a numerical prefactor here that will be different than 2. But for Keplerian potential, this is a very important result that you can check, for instance, for the case of a Keplerian orbit, or the simplest case of a circular orbit in the Keplerian potential. That does it for us tonight. Thank you very much for your attention. At least it is the night for me. I'm recording this on September 27th at 2:22 a.m. in the morning. So now I'm going to take a well-deserved nap while my computer is going to turn these videos into something that is useful for editing. I hope you will really enjoy this video once it gets to you, and I'm going to enjoy working on it. Thank you so much for your attention. Please fill out the quiz, and I'm going to see you in Lecture 8. Bye!